Okay, we're going to continue where we left off with the semantics of declarations. So, one thing that you should think about these rules is that the rules, the thing that you get mapped to on the right-hand side of arrow is kind of the answer of the rule, of a semantic rule. That one's missing an S. And so you can look at the rules and you can figure out, this is the rule, this is going to be a rule for evaluating a declaration, and the meaning is going to be a pair, which is an environment in store. Now, we have, first let me look at what's in the book with Huddle. Let's look at Huddle's rules first and his form. Ours is almost identical. It's just that there's a few features, or there's some. When I went to implement it, first of all, parsing his rules was a problem because something like, let's see if I can think of an example. Like, proc P. Okay, so if I say begin, proc P is skip, semicolon, skip, semicolon, skip. Or, and then end. And then in my version, it would look like, well, the thing is that the ambiguity is that since this is one statement after P, or this is a statement that's after P, and here's the body. So it has to either be that P is defined to be skip, skip, or P is defined to be skip in his. So this is ambiguous. If I wanted the first one in my notation with the in, I'd say proc P is skip, semicolon, skip, in, skip. Or I could write begin, proc P is, skip. Oh, I need a semicolon there. In, skip, skip. So we don't know which program, whether this program is this one or this one with his syntax. So there's no way to tell. So I added the in to specify where the end of the declaration part is. But then another problem I see with his is that his form is that, as I said before, you have to define. I'm looking for that program. Here it is. You have to define all your variables before any procedures. It just seems to me like there's no reason not to allow the intermixing of those two. It's just silly. So here's what he does. He separates them into variable declarations and procedure declarations. And so here's the rule, for example, for variable declarations. Here's this part. If you see something that looks like var x : equals a semicolon, then it has to be, according to him, followed by a DV. So there's a DV. That's more declarations. Could be epsilon next, or it could be that there's more declarations. The point here is that when he declares a variable, he does the following. He says, okay, look, I see a variable declaration, and I need to process that variable declaration and build it into this environment and into this store here. So he says, okay, take the current environment and the current store that came to you with this request to evaluate this thing. Whoops, there should be a little bracket there. And evaluate A using the current environment and the current store and get back the value V. And then to get the new location L, look it up in the environment what the next location is. And then create a new environment envv double prime by taking the current environment and updating so that X, which is the variable that we're declaring here, gets mapped to the location L, which is the new location. And that next gets updated to the new location. So this is what some of this is being taken care of in our allocate function. So that gives you back envv, and that's the one you use up here when you want to evaluate the rest of the things. So now what's built into envv is this declaration, so that the environment for variables says X goes to location L, and when you look up location L over here, he updates the store above the line. The store is the one where L points to V. And that gives you back a new environment, env prime store prime. Oh, it's missing a prime. And those are the values that you return below. So down here, these are the final values that you return. This, I think, is pretty much an exact copy of verbatim copy of his rule. I guess I don't understand certain things, other things in here, like why use this notation that says env with a subscript v, and then use an env without a subscript v. And for the empty declaration evaluated in this environment and this store, you get back just the same environment and the same store. So in my version, we've combined var and proc declarations into one syntactic class. Now, what can we do? Here's the rule. First, what we want to do is we want to say, look, we're going to find two kinds of arrow relations here. One is decals, and one is decal. So decal is the one for an individual list. So what do I do for the individual declaration without any more stuff in it? So it's just var x colon equals a semicolon. I want to evaluate that in the env and in STO. And what do? Well, first I figure out what the value of A is in the current store. The value of A is V. Then I call the alloc function. That gives me a new location and a new store where that location's been initialized. Then I call I update the current environment so that now x, the variable that we're declaring, points to L, that's env prime, and then the store is the store that got created by Alec, updated with L pointing to V, and that gives me back storm prime. And then I just return env prime, which is the updated environment, and sto prime, which is the updated. You know, I could have shortened this. I mean, he was happy to update store up here, so he had this essentially up here. I could have done that. And you could also do env. You could update env up here. That would save some variables and some writing. So anyway, that's what you do when you see the declaration of a new variable is you update the environment that knows which location that variable is bound to, and then you update the store so that it's initialized with whatever A evaluates to. So this is one rule in the decal. We'll end up, there's two things though in decal. We've got the var and we've got the proc. But the proc declaration, the procedure declaration, is more complex because the semantics that we want determines what goes into the environment and how the call works. So to process a list, we do essentially the same thing as him. I mean, we'd say, okay, look, a list of declarations gets mapped to decals. If it's the empty list of declarations, decals just maps it to env and store, which is essentially what he did on the epsilon case up here. And otherwise, if I have a declaration that's a D followed by more declarations, the first thing I do is I take D in the current environment, that's this one, and the current store, that's this one, and I get back some new environment pair, but I'm analyzing it in decal, not decals. So that's the rule below. That's this one down here. This is the decal rule. So I evaluate a var declaration, or I evaluate a proc declaration. And then I get a new environment and a new store, and then I use those to evaluate the rest of the thing, which is recursively going to call this list again in decals. And then I get an environment store prime, and that's the final answer for this. So this essentially, it works the same way. It's just separating out these two things, and now we can interleave them in any way. So, like I said, we'll wait until later to define the rules for proc. The proc rules for both the declaration and the calls, depending on what the semantics are that we want. So consider now we have the declaration semantics. So we know what declarations look like, although we're holding off on calls and we're holding off on proc declarations. So we know what the declarations look like. The calls are actually statements. So what do the semantics of statements look like? Well, it might be worth considering down below here the transition system for statements. So his configurations, gamma, is either a statement paired with a store or a store. And so if it evaluates to the end on the right-hand side, you're going to get a store. T, the terminal configurations are just plain old stores. And you're going to start with something that looks like this. But if you look at the rule up here, we need the environment to be able to figure things out. Like, for example, in this x colon equals a thing, we're going to need to use the environment to figure out how do we assign a value, whatever A evaluates, to the variable X, we need to look up in the environment what's the location. So that's exactly what we do. The first thing we do is we look up in this environment the location of the variable X. We get back some location L. Then we take the store that was given to us initially plus the environment that was initially, and we evaluate A and we get back some V. And so what do we return? We return a store where the location of X gets updated with the value of V. So it's similar to, this X colon equals A looks something like var X colon equals A, but this is, the var form is a declaration. So up there I have to allocate new storage. Down here, I assume I've already got, if the program is sensible, I already have in this environment the location for X. Because before I see this, I've seen a variable declaration for X. So my point about considering this is that, look, the gammas, the configurations are either these things, and the terminal configurations are just the stores. But we need the environment, and so that's where the stuff that he puts to the left of this symbol here, which is turnstile. It's the stuff that you need to figure out the right-hand side over here, but that doesn't actually get modified or updated by these rules in any way. So we see that the semantics for statements, the meaning of a statement, is a store. Now, what I'm saying down here in this section here is that since gamma does not even include env, no statement modifies any environment. You don't change the return value, is not an environment. Declarations are where you build environments. Declarations are the kinds of statements that modify environments. Now, the other rules are all basically the same, except that now they look like, env turnstile. So like the old rule for S1 semicolon S2 in store STO looks the same. First you evaluate S1 and STO and you get back STO prime, double prime, and then you use that to evaluate S2, and then you get back STO prime, and that's the answer. So that looks essentially the same. Okay, but the begin-end block is very, very subtle. It's a subtle thing. So first of all, remember, his looks like this, and ours looks like this. Here's the semantics of mine. They're quite similar to the semantics of his. You can look up the semantic of his begin-end on page, maybe I'm not going to quickly find it. Yeah, I am. On page 87. So see page 87 for Huddle's version. It's almost identical, essentially. Except that he's got more lines above because he's separated out different kinds of declarations. So first he has another spot, another line up here that says, first evaluate the variable declarations. And then in his second line, he says, now evaluate the procedure declarations with the information you got from evaluating the variable declarations. And finally, evaluate the body of the begin. So ours basically says, look, start in some ANV and you want to evaluate this expression. So first thing you do is you evaluate the declarations, and that gives you back a new ENV prime and a new store double prime. And then you go and you evaluate the store S in the store store double prime to get back a new store, and that's the answer. So step 1, process the list of declarations to get ENV prime and STO double prime. Then, using ENV prime, so you're using the updated environment. So this environment that you got back from evaluating the declarations is the one that you used to evaluate S. And the store that you use is the store that you got back. And so you evaluate S, and then you get back some STO prime, and that is the answer. That's what the result of this thing is. But it's a kind of a crazy thing because the store, let's look at this little program here. Here's a very small program. And suppose that I start this in, so this begin here is going to build a bigger environment when we see this, and a bigger store. And then what happens here? We just return this same store that we got from evaluating the meaning here. So what's going to go on? Let's see. I probably should have added some code in here where I used Y down in the body besides on the right-hand side, but also on the left-hand side. So this is a simple program. I'm running it in a program where X has already been declared, and it is, the value for X is stored in location 0, and location 0 has the value 10. So then I start executing this thing. And so what happens down here is I evaluate this rule, which says first, get the declaration. And so the result of that will be a new environment like this. Instead of this one up here, I'll have one that still knows that X is at location 0, but now it also knows that Y is at location 1. It says 11, but it should be 1. I don't think I can get, Why is erasing not working? All right. Whatever. That should be location 1, not 11. Okay. That's a comma. Okay, so after I evaluate this declaration, I have a new environment that knows where Y is and remembers also where X is. And I've got a new store, which now knows that location 0 has the value 10 in it, and location 1 has the value 11 in it. So this is STO double prime. This is after evaluating the declaration, which is going to return a new environment and a new store. So this one here is ENV double prime. Now what happens? Now we execute the body. So the body says x gets the value of x plus y. And so the environment doesn't change when you evaluate our statement. So that I just put double quotes there to mean it stays the same. But what happens with the store is that the store gets updated so that location 0, which was x, now gets the value of 10 plus 11, which is 21. And location 1 does not change. And so the store that gets returned after, now, when I exit, so this is one statement. And after I've executed this statement, the store that I have is this one that says location 0 has 21 and location 1 has 11. But if you notice here, the environment does not get modified by this rule at all. So that rule does not modify the environment, which means that the environment that's in force to execute the next command is the original environment that says x is bound to location 0. So now I evaluate this command. X doesn't change. It's still bound to location 0. And this environment is the same as this one. It doesn't know anything about y. And then the store here is one that says location 1 has 42. And it doesn't, location 0 is 42. And it doesn't change that what location 1 has stored in it. But using this environment here, using this one that you get at the end, you can never look up location 1. It's as good as having location 1 be completely erased. It's gone. It's invisible because there's no environment, there's no variable that's mapped to location 1. So there's kind of like some magic going on here, and it's depending on things. Now, from a security point of view, this could be bad because your program is still keeping in memory the value that was used for y. What if y was some kind of sensitive piece of information? We could fix this by, adding some kind of new operation on stores. We could say okay, look, here's store prime. What if we said that, and here is STO. So we could define an operation that says something like STO restricted to some set A is equal to those pairs X, comma, L such that X is in A. Whoops. Then if I said STO prime, that's this one here, restricted to the domain of the original STO, that would actually be equal to the store that now maps location 0. Location 0 would go to 42. And since location 1 did not appear in the domain of the original store, it's now gone. And so we could do that. We could kind of make any other location that wasn't in the original one change undefined. If you tried to look at it up, it could be an error. So that could be a security issue here because we've still got values from earlier parts of the program floating around in the store. And if you knew what those locations were, you could just look them up. So anyway, next we're going to talk about the scoping rules for procedures. And I'll put that'll be the next video. Okay. Thanks for listening. Bye.